Hello, my name is Brendan Thaler. I'm in Physics 2212, Section N, and this is lab number 2, charge tapes part 2. Before we go into it, I just want to give a quick overview about what we're going to go through. First, we're going to do an introduction to the lab as a whole, and then we're going to get into the physical experiment that we did in part 1, and then we're going to spend a lot of time in the Glowscript model, which is sort of we go into a little bit more in part 2, and we're going to finish up just by concluding and reflecting on some questions. So the purpose of this lab is to calculate the amount of excess charge on a piece of clear tape using Coulombs Law and superposition. So how we did this is we created a charge strip of tape by quickly peeling one piece of tape off of another. We placed a plastic pin near the tape to ensure that it is positively charged. And we do this for another piece of tape to create two positively charged pieces. And then since they're alike, they're going to repel each other. So we put one piece of tape under another until the top piece of the tape is being repelled by the bottom. And we're going to measure the separation between these two pieces of tape, and this is going to be our R vector, the magnitude of our R vector. So the principle behind all this is Coulombs Law, where the force right here is equal to a constant K, which is 9e to the 9, times the two charges over R squared. And so by finding the charge, we can approximate how many electrons were lost using the surface area of the tape and the radius of an atom. And this is going to be equal and opposite to the force of gravity, which we can find by finding the mass of the tape and multiplying it by the acceleration due to gravity. So the calculations we did here, we found the mass of the tape and the way I just said so, and then we have the force of gravity on the top tape by multiplying it by 9.81 meters per second squared to get 0.001946 newtons. We also found the surface area of the tape, assuming that it's a perfect rectangle, we just took length times width. And then using that, we were able to find the number of atoms on one side of the tape, assuming perfect lattice. Finally, to calculate the charge on the top tape, we set it equal to the force of gravity, because since there was no change in momentum between the two tapes, then we knew that the force of gravity was equal and opposite to the electromagnetic force on the tape. And after doing the math we see here in the first four lines, we get a Q is equal to 5.1153 e to the negative 9. And then we did some further calculations to see the charge, how many electrons were removed from the charge tape, as well as the ratio from electrons to atoms, which we see is about 1 electron for every 1.09 e to the 7 atoms. So the vast majority of atoms did not lose an electron. And we have a couple assumptions and limitations here. First, we assume that equal charges are on both tapes. This is probably false, seeing as we did not pull both tapes in the same, like with the same force, at the same angle. So that's a really big assumption to make. We also assume that air resistance is negligible, which is not a huge deal in this experiment due to the tape being so small. The atoms are structured in a perfect lattice so that we can just take the surface area and then the radius of an atom to decide how many atoms were on the face of the tape. And then also we're just going to be approximating the mass based on a ratio of tape length to mass, which could result in a slightly off measure of the force of gravity, which obviously we set equal to the electromagnetic force. So you can see how that assumption can also have a big effect on this experiment. So for the computer model here, unlike lab 1 where we made 2 point charges, this one I actually split it up into more point charges than we had before. So I put it into 40 different point charges so we can have a more accurate model. And so the top is the top pieces of tape, and then each of those green arrows is the force for each of those point charges. So we have 40 point charges, and we're turning that into our model. And so we see we have almost a factor of 10 difference of the electric force and the gravitational force. It's actually smaller, and I'll get into why I think that later. But we can see here, and the Glowscript code will be embedded in the link. It was a little too long to sort of fit on a slide. But we do have the 2 force arrows and then all the individual green arrows, which when you sum those together, you get that white arrow at the top. So some reflective questions. If we model them as a point charge, we would have equal and opposite forces because that was sort of the main assumption we made. But I do think that this estimation is more accurate. Now, there's a difference in estimations because of all the assumptions we made, like, equal charges, and then, measuring them like once they started being repelled, and then obviously like when we're in contact with the tapes, there's a lot of times where the charges are going to disappear. So that's where the main difference in estimations is. And so we know it's not a perfect procedure nor a perfect model to calculate this. A better estimation, I do believe that the summation of point charges is a better estimation because it takes into account the length of the whole piece of tape. And it also assumes that there's an equal distribution of charge across the whole tape. But I do believe that as we break it up into a bunch of point charges and calculate net force there, we will have a more accurate representation of what's truly going on here. Thank you so much.